Okay, this lesson is on 8.6a, polar coordinates. Sorry, this pen is kind of bad writing at the edge of the screen. But it's polar coordinates, and in order to do this, I'm going to have to turn on the grid. So if you don't have graph paper, I would pause this video right now and make sure you have some. You're going to need and want graph paper for the next several days. I'm not going to make this graph paper terribly large, but this should work just fine for us. Actually, I think I can even get away with a slightly less one and zoom out a little bit. That'd probably look better. Okay, so here we are. We learned about three coordinate systems, and it is important for you to know that there are more than one coordinate systems out there. The basic coordinate system that we've learned all about throughout all of school is called rectangular. It's called rectangular because it's defined in terms of left and right and then up and down, horizontal and vertical, or as we're more accustomed to using it, X and Y. Another type of coordinate system involves three variables. We will do this on certain days next semester when people are out for retreat, but it's called parametric. And parametric is basically two equations. You have a variable time, then you have an equation for x that's dependent on time, and then you have an equation for y that's dependent on time. A little different. I know we haven't done it yet. We won't for maybe a while, but it's out there. But this one we are going to do today and for the next few days. This is called polar, where instead of x and y, every single ordered pair is defined by a radius and an angle, r and theta. Now, I'm sorry, theta is defined in terms of radians. We're going back to radians here. So, r, though, is the radius. I'm going to pause here while I switch the calculator back to radians. So here's the calculator that, for me, I left off the last lesson about 5 seconds ago, but you guys will probably hit clear and you have the rest of the stuff in there. Anyway, go to mode, and let's go back to radians. We haven't been there in a while. I also want you to notice that in the mode, you have another option right below radians for function, parametric, and polar. Your calculator will actually be able to graph in polar coordinates. If I hit enter on the polar, and I go to y equals, I now have a new set of ordered pairs. I'm going to be plugging equations in terms of theta. And if I press the X button, it's now going to pop up with a theta. That's one change that we're going to make. You guys can play around with that at your leisure. Let's go back to the grid. I'm going to draw an axis here. Actually, I'm going to keep this on because I'm going to be using this quite a bit. No, not that. There we go. Let's draw a grid. And let's label a few things. So I'm going to start with a ray coming from the center, just kind of popping out wherever. And like before, we have an angle here, theta. And this theta represents a directed angle, meaning something happened. We started here at the polar axis, and that's the new name for the x-axis. And we changed, and we went to a new place. And that's our angle. This ray rotated. We will follow. Counterclockwise is positive, and clockwise is negative. I'm going to use CCW for counterclockwise and CW for clockwise. You don't have to write that whole thing out. And then this ray here has a radius too. R is what we call the directed distance. So we're going to come down here and we're going to practice a little bit with plotting these. This isn't going to be as hard as you think it is. So some examples. Let's plot on the same grid. So I'm going to set up another grid here. And we're going to plot these ordered pairs. 2, comma, pi over 3, 3, comma, negative pi over 4, negative 4, comma, 5 pi over 6, and negative 2, comma, negative 2 pi over 3. Well, you may notice right away that we have a little bit of trouble, because I don't know exactly where these are going to go as well as I might. So we actually need a new kind of graph paper here. This grid is okay. I could draw concentric circles. Here's a circle of radius 1, here's a circle of radius 2, here's a circle of radius 3, and so on, and figure out, okay, oh, I need 1 of 4 because there's 1 with a 4 there. If I do this, I could figure out, alright, pi over 3 is a 60-degree angle, and that's about that, and then 2 away from the center would put it there, but this is just kind of all guesswork. I'm going to pause this for a minute and show you a new kind of graph paper that we're going to use. Okay, we're back, and now this is where you would pull out the graph paper that has been provided. There should be tons of it. And I'm going to start plotting this first order pair 2 pi over 3 on this new graph paper. It's useful to see these next to each other because this graph paper, clearly we're not talking about rectangular grids anymore. We're talking about concentric circles representing radii away from the center and clearly marked angles. Now this one's not so clear to see, but on yours you can probably see it a little bit easier. This should make sense. This is pi over 6, this is pi over 4, pi over 3, pi over 2. And then if you keep going around the circle, you can see all the rest of them. This is also probably a little bit of an easier way of seeing where all the angles are. But if we want to graph 2 pi over 3, note that these ordered pairs, one has to be a radius, one has to be an angle. So let's look at the pi over 3. We want to go 2 from the center. 1, 2. And there's our first point. I'm going to mark it in a separate little spot here. So well, let's not use gray. Okay. Plot the other ones now. In fact, let's do them all on the same circle so we can kind of see how this works. So I'm going to take this and move it off to the side. A little bit. Put it over here. And then let's go second one. Second one we want to do 3 negative pi over 4. Negative pi over 4 is positive 7 pi over 4. It's down this way. 1, 2, 3 from the center would be right here. So that's our second ordered pair. I'm going to label this A. I'm going to label that B. Point C is negative 4, 5 pi over 6. 5 pi over 6 is right here. Positive 4 would be going in a positive direction. 1, 2, 3, 4. So what do you think negative 4 would be? I'll put a dramatic pause here while you think about where negative 4 would go. But yeah, it goes back along the same angle in the negative direction. So if we kind of follow this line along, 5 pi over 6, well, 180 degrees away from 5 pi over 6 is 11 pi over 6. 1, 2, 3, 4. This is where point C would go. Negative radii have meaning here. It means on the complete opposite side of the graph, 180 degrees or pi radians away. Then D, we have negative 2 pi over 3. So, looking at these two, negative 2 pi over 3, I can actually change this angle to say that that is the same thing as negative 2, and if I add 6 pi over 3 to negative 2 pi over 3, I get 4 pi over 3. That is one way to think about where that angle is. Remember, that's the same angle, so 4 pi over 3 is in quadrant 3, right there. But negative 2 pops back up, and look, it's the same point that point A was. If I take this and I add or subtract, in this case subtract 180, I will get pi over 3, and then I make this a positive, You can see that that's actually the same angle as the first one. So points D and A were actually the same point. Okay, now I'm going to skip ahead past all these grids to a new section. Conversion of coordinates. To convert from polar to rectangular. Given a point r comma theta in polar. This is honestly one of the easiest things that you do. You know that r times the cosine of theta r times the sine of theta. That's actually the definition of what cosine and sine mean. So that's the easy one, converting from polar to rectangular. The backwards one. To convert from rectangular, given the xy, to polar. Well, given a point x comma y in rectangular, this gets a little bit tricky. First of all, we have to be very, very, very aware of where that xy point is. So we have to know the quadrant. That's not difficult given xy. Second, the radius part, if you want to figure out what r is, just go back to the squared. That'll tell us what the radius is. And we're just going to assume that the radius is positive whenever we're trying to figure it out. Remember, there are an infinite number of ways to represent an xy point in polar coordinates. We can have an infinite number of angles that are all 360 degrees apart. We can even have some that are 180 degrees apart if they have a negative radius. So we're going to go for the simplest way, which is just going to say r is equal to the square root of x squared plus y squared. Then theta. Here's the theta thing. We know, well, how do we get theta with x and y? Theta is equal to y over x. So theta is equal to the arctangent of y over x. And of course, we know that this will only work if x is not equal to 0. If x is 0, you can figure out where that angle is. Simply, you might know what the arctangent of undefined would be. So that's going to tell us where the theta is. Be aware of quadrants. Look at the xy, match it to where that angle would have to be, and you pick your angle, or you pick your quadrant for the angle. Okay, so let's do some examples of this. To rectangular. There's the ordered pair 4, 5 pi over 6. Now, you may ask, which is which? Well, it's customary, and your book uses the custom of r comma theta. The other way is the one with the pi is usually the radian, so that helps too. Well, converting to rectangular, we know x is equal to 4 cosine of 5 pi over 6, which is equal to 4 times. Now, you can use your graph up here, look way up here, to help you out here. 5 pi over 6, drop a little line there. That looks like 30 degrees, and it has a ratio of 1 to 2 to radical 3. Cosine is x over r, so that's negative root 3 over 2. Let's pop back down here. 4 times negative root 3 over 2. And that simplifies to negative 2 root 3. Y is equal to 4 sine of 5 pi over 6. The sine of 5 pi over 6 is 1/2. 4 times 1/2, or 2. And then I'm just going to express that expression. 3, 2. So So both of these ordered pairs represent the same place, just in different coordinate systems. Okay, let's practice a convert to polar. Here's an ordered pair 1, -1. Thinking about where that is, sometimes it's actually helpful to graph it out, but 1 would be right 1, down 1. That is in quadrant 4. Might want to make note of that to make sure your answer matches. Okay, so now we're going to go r squared is equal to x squared plus y squared and do a substitution. R is equal to 1 squared plus 1 squared. Don't make that negative. Remember, even if it's -1, or if one of them is -1, actually be the y that's -1, that's still -1 quantity squared. So it's the same thing as saying 1 squared. This is radical 2. So r is radical 2. Theta is the arctangent of y over x, so -1 over 1. And the arctangent of -1, look for that place where you have a tangent value of 1. That's 45 degrees, but -1. So we're talking an angle in quadrant 4 that's 45 degrees. Actually, I can even save my work and say 45 degrees in quadrant 4 and in radians. Those are the pi over 4s. So that would be 7 pi over 4. 45 degrees in quadrant 4. So we're actually going to in radian, or in r comma theta. Another application of this is the more difficult one, equation conversion. So I'm actually going to have you graph one of these things. Graph r is equal to 2 times the sine of theta, and tell me the shape. Well, this is going to look a heck of a lot more difficult unless I say, well, let's convert it to stuff we know. I know sine of theta is equal to y over r. If I convert it to rectangular from polar, basically I want to do this for every variable. I can't have r's and I can't have thetas. So that first thing got rid of the thetas, but I introduced another r. That's not good. So how can I get rid of the r's? Well, if I multiply both sides by an r, I get r squared is equal to 2y. Okay, I know what r squared is. I know that r squared is equal to x squared plus y squared. And that's going to be equal to 2y. Now I've gotten rid of all the r's. That's good. But now we have the problem of figuring out what shape this is. Okay, before we do that, let's do a little side plan. There might be some things that you want to write down to help you convert these things. You may want to write down that we're going to be using a few of these in our conversions. Okay. Well, if I look at this, we have an x squared plus a y squared. Regardless of what the 2y is doing, that is a shape we have done. That's a circle. As we go back to the first part of the semester, I have y squared minus 2y equals 0. And then I add both sides. X squared minus 2y plus 1 equals 1. I added 1 so I could make that become a perfect square. B squared equals 1. How does that help? Well, if I compare that to the standard form of a circle, this was the standard form of a circle. This is also good review for the final exam. If I compare that to the standard form for a circle, I know that my HK, also known as the center of the circle, is equal to 0, 1, and that the radius is equal to 1. So, what I'm really asking you is to draw a circle. I can do that here. Centered at 0, 1, with a radius of 1. And there it is. So that's the graph. If you go back up, that's the graph of r is equal to 2 sine theta. Okay, let's try another one of these. You have a section of your homework that actually gives you a few of these, and they challenge you to identify with the code. Well, if we cross multiply, we get minus r sine theta equals 2. I know r sine theta is equal to y. If I go back up, that was how I was converting. If I look at this little cute thing over here, since sine theta is equal to y over r sine theta is equal to y. So actually r minus y equals 2. We just put the r on one side and the y plus 2 on the other, and then we're going to square both sides. R squared is x squared plus y squared. Y plus 2 squared is y squared plus 4y plus 4. And y squareds drop out. So I have an x squared and a y. X squared and a y. Let's keep this like this. X squared minus 4 is equal to 4y. And if I divide by 4, y is equal to 1/4 x squared minus 1. You don't have to graph this, although you could plug this in your calculator to see what this is. I think you guys know what this shape is. I hope you know what this shape is. Y is equal to something x squared minus 1. We haven't gone over how to graph these this semester, although we're going to be doing these again next semester. This is going to be a shape that looks like this. And actually, if I graphed it, it'd have a y, or an x-intercept of -1, and with a 1/4, be pretty wide, but it's a parabola. And I would know the shape is a parabola because in my final form, I had an x squared, but not a y squared. So that's the trick to this. Just use some substitutions. When you're doing the equations, try to get everything out of thetas and r's. Your thetas, you're going to be using r cosine of theta is equal to x, r sine of theta is equal to y. And then your r's, you're always going to want to try to take your r's like we did here into x squareds plus y squareds. Okay, that's it.